My name is Gabriela Cornejo, and this is my video lab report for Lab 2, Lines of Charge. The purpose of this lab was to determine the charge on a charged piece of tape, or U-tape, and we'll have the calculated charge be evenly distributed across the tape rather than just a point charge like we did in Lab 1. This lab will help reinforce ideas learned in lecture about distributed charge and the transfer of charge, and the use of everyday objects will again provide a better visual frame of reference for us to better understand the concepts. The main physics principles used in this lab are Coulomb's law, which allows us to use electric field and charge and to find the electric force on an object using the given formula. The other principle is the law of superposition, which allows us to model the net electric field using multiple point charges, and this is done by dividing an object into multiple components, finding the electric field on each component, and then summing them all together. During this lab, the total charge was determined to be a positive integer greater than that of last week's lab. These values were calculated using derivations of Coulomb's law, the law of superposition, and knowledge on particle charges and their properties. After redoing the floating tape portion of Lab 1, I've calculated the tape length to be 0.204 meters, the mass of the tape to be 0.000204 kilograms, and the distance between the two floating tapes to be 0.013 meters. Based on these measurements, I calculated that the gravitational force on the upper tape would be -2 times 10 to the -3 newtons, and that the electric force should hypothetically be equal and opposite to the gravity because it's the only other force acting on the upper tape. Thus, it should be 2 times 10 to the -3 newtons. Before completing the other calculations for the next part of the lab, some assumptions had to be made in order to do so, such as that the charge is evenly distributed across the surface of the tape. So after dividing the tape into several equal pieces, we can calculate the charge of one point or piece and then multiply it by the number of pieces we've divided the tape into to find the total charge. The other assumption is that the law of superposition can be used to calculate the net electric field and the electric force. With these assumptions in mind, the net charge was calculated to be 3.06 times 10 to the -7 coulombs, which was calculated by dividing the tape into 5 equal pieces, each with a charge of 6.13 times 10 to the -8 coulombs. The next portion of the lab was to create a computational model of the electric fields and forces acting on the upper tape. So after inputting the code into Python, this is what my model looked like, with a magnitude of electric force being 0.0691335 newtons, and the magnitude of gravitational force to be approximately 2 times 10 to the -3 newtons. To generate this model, this is the code I used. So to start off, you have to input all of your constants and observed values, and then put two functions in that will allow you to calculate the electric force later. So the first one is a function for finding electric field, and the second one is the given function for finding a line of charge on the tape. The rest of my code is shown here, where I had to first start by modeling the tapes using the line of charge function, and then calculate the electric field and electric force using a nested for loop and the electric field function I defined earlier. For this part, I also had to create scales to multiply my values by so that it looked better on the model, and after doing so, I could then input the arrows that showed the electric force, the gravitational force, and the electric fields on the tape. And finally, to finish off the model, I printed the values of the magnitude of the electric force and the magnitude of the gravitational force. The magnitude of charge on one piece of tape, as calculated by the computational model, was 3.06 times 10 to the -7 coulombs, and the assumptions made to reach this conclusion were to treat the tape as multiple point charges with the charge spread evenly across the surface, and to neglect any outside forces besides the gravitational force and the electric force of the bottom tape on the top tape. If the tapes had been modeled as a point charge like in the previous lab, the charge would have been 1/5 the size. These estimates differ because the tape is modeled as a point charge in the first lab, and in this lab, the charge is evenly distributed across the surface. These calculations use different methods to calculate charge, hence why they differ. The charge that is evenly distributed across the tape is more likely to be closer to the real value because it more accurately represents the charge on the tape, because tape isn't really a point charge. In conclusion, the results of this lab demonstrated the charge on a charged piece of tape to be approximately 3.06 times 10 to the negative 7 coulombs, and the magnitude of the electric force on this tape was calculated to be approximately 0.0691 newtons by the computational model. Both of these results were calculated using the law of superposition and Coulomb's law.